speaker is an old friend of the house, from Newhouse, and he's going to talk about symbolic extension, same thing as versus CR.
Thank you, Wellington. Without the mic is okay? Or is it better with the mic? It makes no difference to me.
We can hear back here.
You can hear fine. Okay, great. So let's do it this way. Well, it's a great pleasure, as always, to be back here at IMPA, especially to celebrate this 50th anniversary. I have many, many happy memories of both friendly relations and interesting and stimulating mathematical.
Excuse me, I think it's better to use the
Because we are recording and transmitting it to the internet.
So this gets attached. Comme ainsi.
As higher as you can.
Ainsi?
Yeah.
Ok. Tá bom?
Okay.
E esse aí vai ser onde? Esquerda, né? Ok. What was my suggestion? Oh, well, yeah, no, I always cause problems for myself, so otherwise life is too easy, and I don't want it to be too easy. So in any event, it's a great pleasure to be back here again, see my old friends, new friends I make frequently, and to have the opportunity to talk about some things actually that are related to a number of discoveries that I made when I was here at various times. I also have the benefit in this lecture, I feel like I'm a movie star. Here at the dark, here I am at the light, and so on. I won't sing or dance yet, but keep that, then you have something really to laugh at. But in this lecture, what for the experts, basically what I will be doing is some elementary remarks on some substantial work of other people. But in fact, I want to make it understandable to the audience as a whole, so I will be elementary in certain things. This is joint work with Tomas Donarowitz, who visited us at Michigan State this spring, and this work actually arose from some very stimulating lectures that he gave about his recent work with Mike Boyle. I'll get into the description of those things in just a few minutes. But it struck a chord, as you will see, with some old familiar things that I had been involved in a number of years ago. So first of all, as is usual in dynamical systems, so just the general setup of the story. So we'll start initially with, is it changing? This is a dynamical overhead projector where the focus changes, or, okay. We start with a compact metric space and a homeomorphism, self-homeomorphism of the compact metric space. And what we are looking for are some nice class of models of dynamical systems that are understandable in some sense, that mirror as much as possible, and we'll be more precise about what we mean by that, the dynamics of our given space. So the first example, well-known example of simple models is the so-called full shift on n symbols. So here we take an alphabet of n letters, and we look at the product over the integers of that alphabet. So typical elements are written as sequences, doubly infinite sequences, and we consider the shift transformation, which takes a given sequence, indexed, and moves it one unit to the left. So that's a homeomorphism of that compact metric space, and it has some very interesting properties. I'll describe those in a few minutes, but first, the second example, somewhat more specialized with many of the same kinds of properties, is the so-called subshift of finite type, or topological Markov chain. And here we take the full shift space, that is the full symbolic space, but we only allow certain kinds of words that appear. And we do it by specifying an n, so the alphabet has n letters. We take an n by n 0, 1 matrix, so-called incidence matrix, and then look at all of the doubly infinite sequences with the property that the matrix at index ij is 1 for every pair of indices. So the matrix, if we have the symbol a sub I doubly running through the integers, then the matrix A sub I of adjacent points is 1 all the time, and it's elementary to see that this is a compact sigma invariant set with also some very special properties. Now we want to be somewhat more general and look at arbitrary symbolic sets, which in fact can be very diverse and have many, many peculiar properties, but nevertheless they do have some real structure, as we will see in the course of the lecture. And ask the question, so an arbitrary symbolic system is simply a closed shift invariant subset of the full shift. No finiteness properties in its definition or anything. You just take an arbitrary closed invariant set. And we can ask, in some sense, what systems can be modeled by an arbitrary closed subshift, and what properties do such systems have. First of all, we have to be a little bit explicit about what we mean by model. Of course, in dynamical systems, the standard model, which is a little bit too restrictive from our point of view here, is to say that a system has a good model if there's a topological conjugacy between the model and the system. So precisely that means that we have two systems f and x, fx, f on the space x and g on the space y, and we have a homeomorphism from y to x, which carries the dynamics of the system on y to the system on x in the sense that this diagram commutes. So with a homeomorphism. Now, in the case of trying to find wide latitude in describing our systems, this is obviously much too restrictive, because these, that is to get symbolic systems which are conjugate to general systems, because symbolic systems have dimension 0, and a conjugacy is a homeomorphism. It will preserve the dimension of the space. That's the first kind of objection one would have to strict topologically conjugate symbolic models. The second is that shifts are expansive. That is, points whose orbits stay close for a long time in the future and past are the same point. That's what expansiveness means. So we have to weaken the notion a little bit in terms of what we mean by a model. And the first natural weakening is to take the notion of an extension. So instead of having the equivalence or the mapping from the carrying one space to another be a homeomorphism, we just let it be a continuous surjection. And obviously, what we would like to do is get it in some sense as close to a homeomorphism as we can, depending on various... we have a dual problem here. We want it as close to a homeomorphism as we can get it. That makes it more restrictive in terms of the classes we can model, so we want a suitable definition that we can use. So first, the standard notion here is when you have a continuous surjection carrying a system gy onto a system fx, is to say that fx is a factor of gy, or that gy is an extension of fx. So then the question I want to raise or consider is which systems have a symbolic extension? And secondly, how close to a homeomorphism in a certain sense can the symbolic extension be picked? Okay? And a first condition which is really necessary, and I'll remind people of these definitions a little bit later, is that this invariant, a standard invariant in dynamics called the topological entropy, be finite. If we have a symbolic extension, then we have finite topological entropy. Okay? So I now want to describe what I mean by closeness or good. This is an obstruction here, I see. Okay. So I'll get the hang of it in a minute or two. Okay. I'll say that one system is a principal extension of the other if it's an extension and the fiber dynamics, the dynamics that sits over every point that gets translated, is simple in some sense. And the simple notion I want to talk about is that the fiber will have 0 topological entropy. So in words at this point, it means that there is a exponential amount of complexity in the ambiguity. So you think of the base space as coding subsets of the fiber. You have a surjection, take the pre-image, these subsets are moved around, and the complexity in the subsets that are moved around is sub-exponential. But I'll be a little more precise. So there's no fiber complexity. That's the notion of a simple principal extension, symbolic extension. And now it's worth noticing First of all, that this will not preserve much of the topology. If you take an isometry, distance-preserving homeomorphism, that will have no entropy. So as a consequence, if you take any given system and take the product with an isometry, then you'll have a principal extension in this sense. So that somehow shows that, at least that in the that we won't preserve topological information, but in some sense we preserve dynamical information up to a sub-exponential amount of complexity. So it's a fairly general kind of thing, and so the first natural question is, why would you even look for symbolic models? What can you hope to gain from such things? And so let's go back then and visit some of the shifts that we have, general shifts, and talk about some of the kinds of good properties that they will have. And I'll define these concepts for the benefit of the non-experts in just a few minutes, because we will use some of the detailed properties of topological and metric or measure theoretic entropy. But the shifts have fairly good properties, especially continuity properties with respect to these invariants. And so one would expect, therefore, that using such models you could describe or understand other systems in a pretty good amount of detail. So let me now just briefly remind you of basic definitions of these invariants. This is obviously for non-experts. So what is topological entropy? So we have our homeomorphism. What topological entropy roughly measures is counting orbits with a certain precision. So you give yourself a precision epsilon, and then you say that 2 points have the same n orbits up to epsilon if, as you move along the first n iterates, they never get epsilon apart. So if you were looking at something with epsilon precision, you could not separate the points. And now what you do is you consider the number of distinct orbits in that sense. The number of points, 2 points will be distinct if in their trajectories up to time n, they separate by epsilon. You consider the number of those and the exponential growth rate of that as follows. So a subset of my space is called n epsilon separated. So n's a positive integer, epsilon is a positive real number. If any 2 distinct points in the set are epsilon distinguishable somewhere between time 0 and time n. So the orbits get separated by epsilon somewhere in between. And then what we do is it's elementary to show in a compact metric space that the number of such points, the maximal number of such points, is at most exponential. There's an exponential number. So you take the best exponential estimate for a given epsilon, and that's called the topological entropy of the set of size epsilon. That is the growth rate, logarithmic growth rate, lim sup 1 over n log of the maximal cardinality of n epsilon distinguishable orbits. That's the entropy of size epsilon. Then we let epsilon get smaller and smaller, and we get something that depends only on the set. That's the entropy, topological entropy of the set, and then the topological entropy of the whole map is where the set is everything. And it's useful from our point of view to consider sets K which are not invariant. So now, in the sense of symbolic description or looseness that we were talking about before, if we have a principal symbolic extension, it's a fact that on the fibers there will be no entropy. The entropy will be 0 as we move along. So in some sense, that's our notion of closeness. Well, there are some well-known standard properties of topological entropy that I want to summarize briefly. First of all, it behaves well with regard to powers. The entropy of f to the n is n times the entropy of f. If you have an extension, g of f, the entropy is bigger, no smaller, that is bigger than or equal to on the extension. It's a topological conjugacy invariant as a consequence of this, because if things are topologically conjugate, they will be extensions in both directions, so then we have equality. And it behaves well on products. The entropy of a product is the sum of the entropies. Here is a less obvious, again, fairly well-known concept, where we bring in some smoothness into the description of entropy. If you have a C-infinity map of a compact manifold, there's a geometric way using the smooth structure to describe the entropy, and it's simply the following. You take an embedded disk of a certain dimension in the manifold, You iterate it n times and look at the, if the disk is dimension k, you look at the k-dimensional volume counted with multiplicities and watch how that grows geometrically. Then the largest volume growth of disk is in fact equal to the entropy. And here there's the again, known remark that this is a C infinity theorem. It is not true for finite R. There's a defect in finite R. In finite R, you have an inequality that entropy is less than or equal to volume growth. But to get equality, you really need to make use of the smooth structure. So just to illustrate geometrically what that means, well, first, before I do that, again, in the standard algebraic models, we have simple ways to compute the entropy. The entropy of the full shift is just the log of the number of symbols in the alphabet. The entropy of a subshift of finite type defined by matrix is the log of the largest eigenvalue, absolute value of the matrix, the spectral radius. And for an arbitrary shift, the way you can compute the entropy, topological entropy, is by the growth rate of the number of n blocks for various n's. Take the logarithmic growth rate. Those are standard facts. Using the theorem about volume growth rates, we can estimate entropy for smooth systems in a fairly simple and understandable way. If we have a map, a horseshoe-type map, like this, that folds over twice, then notice that in such things, if it's sufficient to compute the length growth of curves, the maximal length growth of curves, and you easily see that if you have a line segment going from the bottom to the top, such as in this blue gamma, a curve like that, its first image is doubled. So the first time you iterate it, the length will be twice, at least twice roughly this length. When you hit it twice, entropy in this picture will be log, that is in the invariant set. Of course, if we start with maps that iterate several times, we get an analogous statement. If we have a given rectangle mapped 3 times, so the number of components of intersection in the surface is 3, the entropy would be log 3. Again, for 4, the entropy would be log 4. And so I want to relate that geometry a little bit to the following kind of observation. Suppose now, this is again examples using the geometry of length growths, which we'll return to a little bit later. Suppose we have a hyperbolic saddle point in the plane with unstable and stable manifolds which are tangent actually along an interval. Then with small perturbations, we can introduce a lot of little wiggles near the tangency. That's what this picture is. And then if we look at rectangles that sort of go across many of these wiggles, so this picture here is supposed to be an enlargement of local properties here, you see a rectangle which under a lot of iterations will stay near the fixed point, eventually come up to a place like this, and after a moderate, in fact usually 1 or 2 or finite number of returns, come back to a lot of wiggles. So the return map will have large entropy. The return map will have entropy, basically it will be one of these multiple type of horseshoes, the number of components, the log of the number of components. But if we want to look at the entropy produced for the original map in this kind of construction, what we're forced to do is consider the orbit of this and the whole and the time of return, and then you see a fairly elementary calculation that the entropy of the orbit of the so at the return map I have f to some large return which looks like this multiple component horseshoe. If I look at the largest invariant